Hey everybody, this is Mr. Beckstrom, and today we're going to take a look at section 3.5. This is derivatives of trigonometric functions, and we're going to start with a couple of special limits. And let's see why. I'm going to do the first one here, and I'm going to leave the second one as an example in the book if you want to take a look at that. But with the first one here, we have the limit as x approaches 0 of sine of x over x. And they're saying that that is equal to 1. Well, let's go ahead and see if we can take a look at this before we decide that it's equal to 1. So if I were to put the 0 in there, replace it in here, I get the sine of 0 over 0, which is 0 over 0, which is the indeterminate form. So that tells me that I have to keep going. Now the next thing I want to do is I want to look for ways that I can maybe factor out an x from the top, but it doesn't appear that there's a way or using a trigonometric identity in order to factor out just an x from sine of x. So normally we would go by that approach. We would maybe try to factor something out or use a trigonometric identity or something so we can cancel this x out down here, so then we can reapply the limit. But in this case, there is not an easy way to do it. So the first thing I would probably do is take a look at it in the calculator. So let's do that now. Alright, so since we're graphing with trig functions, we need to make sure that our mode is in radians, which it is. And then we're just going to get the y equals, and we're going to put in sine of x divided by x. So sine of x divided by x. And let's take a look at this graph. And remember, we're trying to find the y value as the x value approaches 0. So if I graph here, and let's do a much smaller window. Let's go to -2 to 2 and -2 to 2. -2 to 2. And that will get us right around where that x is equal to 1. And if I look at x equals 1, I can see that it looks right at y is equal to 1. I can use the trace function for that if I want to. So get x at 0, y is equal to, see now, look at this. The trace value is not showing me a value there. And why is it not showing me a value? Well, it's not going to show me a value because x is, 0 is not in the domain of this function. Why? Because a 0 for x would give us a undefined function for y. So there's really a hole right there, and one of the drawbacks to the TI-83, TI-84 calculators with 30-year-old technology is that they don't show you the holes. Not like a big hole right there or anything, but there is a hole there, and that's why it's not giving you the y value. But remember, we're only looking for the limit, so we don't care if it's defined at 0. We just care about what y value it's approaching from both the left and the right. We can see just a little bit to the right of 0, 0.03, we have a value of y that's really close to 1. And if we look from the left, -0.03, we can see that that value is also really close to 1. So this would give us great graph kind of evidence that the limit is actually equal to 1, but it doesn't really prove it. So the proof is on page 171 in the book. I'd love you to go take a look at that and see how well you can follow it. It uses the squeeze method and a bunch of properties of triangles. It's a pretty intensive proof, something that you will definitely see if you wanted to keep in the math field here, but it's not something that I'm going to go through step by step for this class, but definitely take a look and see if you can follow it, see if you understand the steps. It's pretty intensive here. All right, and then kind of a similar stuff for the limit as x approaches 0 of the cosine of x minus 1 over x is equal to 0. And we just have to have these two special limits kind of in our toolbox here, because sometimes we'll need those in order to solve some examples, just like the one we're about to look at. We have the limit as x approaches 0 of sine of 5x over 3x. So go ahead and see if you can apply either of these special limits here in order to solve this. One little trick, remember, the angle here is 5x. So in order to use this, we would have to have a 5x on the bottom. So see what you can do, and then we'll go over it. So unpause the video when you want to do the solution. Okay, so what we need to do here is get this into a 5x. So we have to multiply both the top and the bottom by some number that'll change 3x to 5x. Or, and this is the way I'm going to go ahead and do this one, this is really just a 1/3 that I can pull out in front of the limit. So if I pull that, 1/3 out, it's going to look like this. There's my pen. 1/3 times the limit as x approaches 0 of sine of 5x all over just x, because I pulled that 3 from the bottom out, so there's a 1/3 out there. Now I can multiply both the bottom and the top by 5, so that way I get the angle to match what's on the bottom. And now I can just pull the 5 out of the top, so that's going to be 5/3 times the limit as x approaches 0 of sine of 5x all over x. And we can actually see here that this 5/3, if you were to multiply the 5/3 by the 3 down here and the top by 5/3, that would have also given us our 5x here, and then we could have just pulled the 5/3 out. So either way, we're getting a 5/3 out here. And now, oops, I forgot to put the 5 in there. And now we have the sine of an angle over the same value there. And I can use this right here. So the limit as x approaches 0 of the sine of an angle over itself is just equal to 1. So this is going to be 5/3 times 1 is equal to 5/3. And that is going to be our answer. And if you want to, you can take your calculator, put this function in here, take a look at x equals 0, and you should get something that's very close to 1.66667. All right. So let's take a look at the trig functions, the derivatives of those. All right, so here are the derivatives of all 6 trig functions. So the derivative of sine of x is cosine of x. Derivative of cosine of x is negative sine of x. Tangent of x is secant squared of x. Cotangent of x is negative cosecant squared of x. Secant of x is secant x tangent x, and cosecant x is negative cosecant x cotangent x. So how did they come up with these derivatives? Well, for example, the tangent of x can be written as the sine of x over the cosine of x, and then we can apply that quotient rule that we did. Remember, the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared, and you'll eventually get secant squared of x. So there's different ways that they show each one of these. And you can take a look in the book there for each one. It starts on page 173, and then they look at the derivative of the sine and the cosine, and they're actually using the limit definition of the derivative in order to show those. All right, so let's look at a couple of examples here, and we'll go right here. This is number 26 in the exercises of section 3.5. And remember, we're probably going to end up having to use things that we've done before. So let's see if we can give it a try. So we have the sine of x plus 4 times e to the x. So go ahead, see how far you can get, and then we'll unpause the video, and we will go through the solution. All right, so remember the derivative of the sums, we can break this into this. We'll find the derivative of sine of x and then the derivative of 4e to the x. So this is a pretty easy one here. So y prime is equal to, this is derivative notation, so the derivative of sine of x is just cosine of x. Cosine of x. And the derivative of 4e to the x, remember the derivative of e to the x is just e to the x. And the 4 you can pull out and put back in, so we're just going to end up getting 4e to the x. So nice and easy one there. So let's do a bit of a harder one. Okay, here we have y is equal to x times the sine of x all over 1 plus cosine of x. So here is one that I very well might put on a test, and it will definitely use different rules here. So pause the video, try it out, and when you're ready, go ahead and unpause it. Alright, so the first thing I can do is I can set this up as a quotient with a function over a function. So I'm going to call this whole function here the top, and this whole function here the bottom. And then, and we're going to need quite a bit of room for this one here, then we have our quotient formula for derivatives, which says y prime is going to be equal to, and we do the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And that is from section 3.4, I think. Yes, the quotient rule. All right, so let's see how we're going to do this here. So we know that the top is equal to x sine of x, and the derivative of the top is equal to, we're taking the derivative of a product here. So we're going to have to apply the product rule, which I'm going to go ahead and do off to the side here. So t prime is equal to, and if we remember the product rule, that is the first times the derivative of the second, the derivative of sine. You can look up there, but it is cosine of x. So x cosine of x times, or excuse me, plus the second term, so that would be sine of x, times the derivative of the first term. The derivative of x is just 1. So this is what the derivative of the top is. So I'm just going to put that in here. X cosine of x plus sine of x. And then the bottom is going to be 1 plus cosine of x, 1 plus cosine of x. And the derivative of the bottom, well, we can break this up using the sum rule. So the derivative of 1 is just 0. So we're just looking for the derivative of cosine of x, which up there is negative sine of x. And I will show you, just so you believe me, cosine of x is negative sine of x. Alright, so now that we have it all broken down here, we're going to basically be applying this rule up here. So y prime is going to be equal to the bottom, which is 1 plus cosine of x, times the derivative of the top, which is x cosine of x plus sine of x plus sine of x. And then we're going to have a minus the top, which is x sine x, x sine of x, all over the derivative of the bottom, which is negative sine of x. And this is all going to be over the bottom squared. So I just leave it in that form. 1 plus cosine of x quantity squared. Whew. And as you can guess, we need to do a lot of work to simplify that. So let's go ahead and do that because I think it's good practice here. So y prime is going to be equal to, I can FOIL this out, so it's going to be the first terms, so that's going to be x cosine of x, and then we do the inner terms, so we can do those next, so that'll be x cosine of x times x cosine of x, so that will be plus x cosine squared of x, cosine squared of x. And then the outer terms, 1 times sine of x, which should just be sine of x. And then the last terms, cosine x times sine of x, is just cosine x sine of x, cosine x sine of x. And I'm running out of room already. And so this is going to be minus, but we have a negative there, so that'll end up becoming a plus. And that's going to be x sine of x times sine of x, which is x sine of x, sine squared of x, sine squared of x. And then on the bottom here, we are going to have the 1 plus cosine x quantity squared. And we could almost leave it like this, except I see one little thing. Notice that we have a, I'm going to kind of do this off to the side a little bit here, but I have an x, oops, I have an x cosine squared of x plus an x sine squared of x, sine squared of x. Y'all can let me know if you saw this here. But if I factor an x out of those two terms, I'm going to get x times cosine squared of x plus sine squared of x. And that's just equal to cosine squared of x plus sine squared of x is equal to 1. So that's x times 1, which is just equal to x. So this term here and this term here, so that term and that term, those just become x. So we can finally write this as x cosine of x, and then those two become just plus x, and then we have plus sine of x, so plus sine of x plus cosine x sine of x all over 1 plus cosine of x quantity squared. Man, that was a killer, huh? Now, I would probably take this if it was on a test and give you full credit. But I would be impressed if you saw that you could reduce those two terms into just x as well. So, all right. Well, I think that's it for today. Make sure you try through some of these and the exercises in my math lab and additional exercises in the book if you want to look at more examples. And if you have any questions, please let me know, and I hope you have a great rest of your week. Thanks.